Hey, good morning, everyone. Thank you, Kerry. My pleasure to be here. So over the next 45 minutes, I'm going to try to walk you through some examples of how the distribution system is planned, how utilities expand their systems to meet changing demand and to ensure satisfactory performance for our consumers. Some of the fundamental objectives and the constraints, the activities involved in effective planning, I will illustrate them with examples from an IDP, an integrated distribution plan filed by Xcel Energy. It's specific to Xcel, but some of the, I'm sorry, I just had a pop-up about share my webcam. But they will be certainly applicable to your regions. Kerry, question, am I driving the slides or are you driving them?
Yep, just let us know when you want to go to the next slide. Just say next slide, and we also know that you have some polling questions before you get started.
Okay, so you want to go ahead and administer the poll now?
Yep.
So the question, as you're seeing, is where the most interruptions occur on a typical U.S. power system? Generation system, transmission, the substation, the distribution, including the feeders and the laterals, or the customer premises, including the service drop and the actual customer connection. Make your selection now, I suppose.
Yep, and we're waiting for about 50% of the folks to submit answers. We're just under that right now, so we'll give it another 3 seconds.
Okay. %93% selected distribution, and 93% of you are correct. About 70% of outages that impact customers are attributed to faults on the distribution system. You may be surprised at that number. Many of you actually are not surprised. And so this kind of heightens the importance of what we're discussing and why it's so important to plan the systems correctly and operate them so that customers achieve the best satisfaction. So thank you for participating. Next slide, Kerry. So a good distribution planner must do 3 things. They must identify the goals for the distribution system performance. They must understand how the differences in system design and the equipment that is deployed will affect the achievement of these goals. And they must find the optimal in quotes, design to meet system performance goals. Goals, as I describe them, include several things. There is a goal for frequency. The distribution system must deliver power with required frequency in the US, that's 60 hertz. Note that distribution systems are not typically responsible for the frequency of the system. That's typically from the bulk power system, from the generation side. But in a microgrid, for example, the distribution system of the microgrid will be responsible for regulating frequency. The system must deliver voltage with appropriate regulation, typically within plus minus 5% of nominal. Must deliver adequate availability to the customer. And availability is another term for reliability. And it simply means deliver power to customers when they require it. In the US, the typical availability is that customers have less than 2 hours of outage out per year. 99.98% of the time, customers have power. And the system must also deliver adequate capacity to meet the instantaneous demand. As we know, load and generation demand must be balanced, otherwise things can happen in the system, including frequency deviations. And overall, the system must reach all customers wherever they exist. The distribution utility is often the provider of last resort, and so there's a delicate balance that must be met between performance and cost, and this balance is affected by a number of challenging factors, including customer satisfaction, performance pressures, regulatory mandates, and so forth. Next slide, Kerry. So why do we plan? Well, we plan because it takes time to prepare and build an facilities. For generation, to build a generation plant, the lead time is typically 13 to 15 years before the plant can go in service. If you move down the system towards extra voltage transmission, sub-transmission, it takes less time. But even at the distribution level, it takes several years to put a substation in place. It takes 3 years to put a feeder in place. So as the load is expanding, as you are connecting your customers, as customers are changing the modes of operation, you need to project, you the planner need to project forward and see when you would have a contingency situation, when you would need to expand your system, and plan before that timeline is exceeded. Obviously, no action means the plan is to do nothing. That's also an effective plan, depending on the situation. But oftentimes, these lead times drives the planning time frame. Next slide. Loads are the primary drivers of most planning activities. On the left is a daily load shape, such as you would find, for example, on a feeder. It appears to be fairly smooth, it's continuous, it's somewhat intuitive. You can look at this load and you can correlate it to what's happening. In the morning, there's a minimum load. During the early morning time, the load is rising as economic activity takes place. It hits a peak sometime in the late afternoon, and then it declines until the nighttime activity is done, back to the minimum load. This is fairly typical of load that's aggregated at a higher level, such as at the feeder and the power transformer, the bulk power system. I'm still on the same slide, sorry. On the right slide, you see the load at an individual customer location. And as you can see, this is dramatically different from the aggregated load. There are spikes and there are peaks and there are discontinuities. And this is due to the fact that things happen in a home sometimes instantaneously. And the key thing is that customers are diverse. No two customers are the same, or behaviors are different. And so that when you begin to aggregate multiple customers together, the spikes of one customer may fit into the gaps of another customer's demand. And as you move further up the system, from an individual home to, for example, a distribution transformer to a feeder, you begin to see a more continuous shape. The perceived variability depends on the level of aggregation, but it also depends on the resolution. Are you looking at the load at an hour level, or are you looking at the load every half an hour, every 15 minutes, every second? These loads, which vary in time and space, drive our planning activity. Next slide, please. So as I mentioned, I will illustrate the various elements for the long-term distribution plan that's driven by the load activity by walking through an actual plan from Xcel utility. Xcel Energy is a multi-state utility. It has an operating area in Minnesota called Northern States Power, Minnesota. They are mandated to file an integrated distribution plan every year in November. I will be looking at the November 2019 plan for illustration, and also taking some things from the 2018 plan. So the 5-year action plan on the next slide was developed to drive the grid investment decisions for the utility over the 5 years from November 1, 2019. The plan is focused on providing customers with safe, reliable, and affordable electric service. In fact, this is basically the mandate from Xcel that the backbone of our distribution planning is to keep the lights on safely and affordable. It's a nice tagline, but it kind of encapsulates everything they do. The plan is also focused on advancing the distribution grid with fundamental and foundational capabilities, and for procuring and implementing an advanced planning tool. And this is quite important. I'll go through a little bit later what the aspects of this advanced planning tool are. But to say the least, it's necessitated to facilitate non-wise alternatives integration, load forecasting, scenario analysis, and integrated T&D resource planning. Next slide, please. The company's strategic priorities, the next slide, thank you, are embedded in just about all aspects of the distribution planning. The priorities to lead the clean energy transition, to enhance the customer's experience, and this goes directly to the heart of the performance of the distribution system that is enabled by the plan, and to keep the customers bill low. And those priorities on the next slide basically lead to a distribution planning framework that is essential for ensuring safe, reliable, and affordable electricity. The work performed by the distribution planning and operations, because that's an essential part of the system performance also, but we're focusing on planning. The work performed by distribution planning is essential to providing the safe, reliable, affordable electricity. However, in addition to the traditional activities that are required to maintain and extend the electric service, the distribution department is also charged with transforming or modernizing the grid as part of the so-called Advanced Grid Intelligence and Security Initiative, or AGIS. And so this AGIS is basically another name for the grid modernization efforts that are being undertaken at Xcel Energy that build on top of the traditional distribution planning activities. And that's kind of one of the things I want to drive home today. And I'm going to say it several times, that distribution planning, traditional distribution planning, is essential to providing customer service and the performance required for customers. But the grid modernization aspects need to build on top of the traditional planning. The so-called muddy boots things, the expanding the system, sizing the transformers properly, routing the cables, trimming the trees, inspecting the poles. These things are foundational and have to be done before the realization of grid modernization is achievable. So the AGIS initiative is around enhancing the security, integrating more distributed resources, supporting electrification, and enabling improved customer products and services. The overall approach to system planning is proactively identifying the existing and anticipated capacity deficiencies or the constraints that could lead to overload. For the next few slides, I will focus more on system overload and how to mitigate those as an example of how this process works. But later on, I will talk about other aspects of distribution planning. So an important aspect of planning is the process of analyzing the system's ability to serve existing and future customers by evaluating the historical and the forecasted load levels and the utilization rates of equipment, such as transformers and feeders. Xcel Energy and most utilities that have high DER penetration see this changing as the planning process evolves from just analyzing future electricity connections, from just analyzing future loads to analyzing future electricity connections, which include DER, electric vehicles, and other non-traditional loads. And so as the planning process evolves, non-wise alternatives than DER becomes a major part of the challenges and the opportunities for distribution planning. Next slide, please. So in the next couple of slides, I will walk through this cyclic annual distribution planning process, which starts from the load forecast and goes all the way to design and construction. In Xcel Energy, the process is initiated in the fourth quarter of each year using the current year estimated peak loads and the historical peak loads for the past 5 years to forecast the load, and then that goes into risk analysis and developing mitigation plans. So on the next slide, I will talk about load forecasting specifically. But before I do that, let me say a little bit about the typical distribution system design that you would see at Xcel Energy or just about any utility in the US. Distribution feeders are typically designed to be radial circuits with one path of flow from the transformer, from the substation, down to the end customers. Xcel has about 5,000 miles of overhead circuits. And you can be sure that the vast majority of these 5,000 miles of overhead circuits that are on several 100,000 poles are radial lines. And on a radial distribution circuit, the failure of any component, any single element along that series of connected elements will cause a customer outage. So on the slide that you're seeing, you see that the feeder main line is basically the three-phase part of the system, and the fuse tap goes off to a lateral, and the customer is shown by the house graphic. Radial path can be traced from that customer through the secondary service, which is the purple, through the fuse tap, on the lateral, and then onto the main line back to the substation. Any failure along that path would cause an outage for the customer. Now, you might say, why would anyone design a system like this so that any failure would cause an outage? Well, two things, really. It's cheap, and it's easy to maintain and repair. The backstop for failures on a radial distribution system is to design backfeeding or ties between adjacent circuits that will allow the utility to transfer customers from a circuit that has failed to a circuit that's operating, and thereby mitigating long outages for customers. In Xcel, the system is planned so that these single continuously switching operations can be done within an hour, and so customers can be restored within an hour, and while they're waiting for the feeder to be repaired, and then they can be switched back to the main feeders. So keep this in mind as we go through the discussion, that these overhead lines fail, but when they do fail, they are switching operations that are planned and designed to mitigate those failures. So with a typical system design in mind, the planning criteria can now be contextualized around this. The planning criteria is such that voltage at the customer should be within 5% of normal. The voltage imbalance should be less than 3%, so they design the system so that the voltage is balanced in all three phases as much as possible. Current flow in all three phases should be balanced such that there is little or no current flowing in the neutral for a three-phase connection. The feeder loading on the N-0 so-called normal or system intact conditions. So that is the conditions when there are no faults on the system and all feeders operating. The feeder is designed so that each feeder is loaded to 75% of its capacity or less. And there is additional and adequate ties between each feeder and its neighbors for N-1 contingency situations. And N-1 is when there's a fault and you have to transfer customers from one feeder to the other. So the image that you're seeing on the bottom shows a feeder that has 75% loading on each of its segments. When a fault happens, so that yellow lightning bolt at the top is the fault. So if that feeder fails, let's say a tree falls across the line, or transformer blows up or something, then the entire feeder is out of power. Because remember, it's a radial feeder and power only flows from the head to the tail. So the entire system is out of power. And now the mitigation options become I need to transfer customers from that feeder to alternative feeders. So the customers on section 1 that's loaded at 25%, that 25% of load can be transferred to feeder number 2 via that tie. The customers on section number 2, the middle section, can be transferred to feeder number 3, and the 25% loading on section number 3 can be transferred to feeder number 4. And the assumption is that feeders number 2, 3, and 4 are loaded at 75% and therefore have the capacity to pick up 25% of the loading from the feeder that's faulted. When the total feeder circuit utilization in a study area exceeds 75%, then this transference of load is no longer effective, and more elaborate solutions now need to be employed. Next slide. So that takes us into some of the more extensive distribution planning mitigation measures. The load forecasting now is the first step, and the forecasting is done by using the load for the previous 5 years and applying a growth factor and projecting what the load would be in the future. Demand is forecasted at both the feeder level and the substation level, and then aggregated up to resolve with the corporate forecast. A number of factors are included in the analysis, and they're shown there. Historical load growth, weather history, customer plan additions, circuit reconfigurations, and so forth. But again, the goal is to generate a 5-year forecast for the system. The next slide shows an example of how this is done for feeder. So on the next slide, which is taken from the 2016 study that was filed with the 2018 plan, it shows that a feeder, 11 13.8 kV feeders, and 2 34.5 kV feeders in a focus study area. The load for those feeders were forecasted into the future to evaluate whether measures need to be taken for circuit overloads. As you can see in the blue line, the blue trace, historically there was not an issue for the feeder. And then in around 2015, they looked at the load for the previous year and applied a 1% growth rate to get the top dash line and the 0.5% growth rate to get the bottom dash line, which is a conservative forecast, and so projected into the future what the load would look like. Next slide. The next slide shows similar type of forecasting for a substation. And this is for a 13.8 kV substation transformer. And you can see the substation transformer's load was typically below the red line, which is the transformer capacity, N-1 transformer capacity, which would be the line where something needs to be done. So historically, it was always below that line. Sometime around 2015, there was a load increase from a large development, and that now impacted the load forecast going forward. As you can see, the load forecast jumped dramatically from about 2015 onward, and such that when you project into the future, around 2018, the substation load would exceed its thermal capacity limit on an N-1 continuous situation. That is, when a fault happens and you have to transfer load to the substation, it will be overloaded beyond its thermal capacity. And so therefore, this will require distribution planners to develop mitigation measures for this substation. So to summarize, the forecast really exposes whether there is a trigger for doing something about your feeder capacity or your substation capacity. By projecting what the load increase would be in the future, you now begin to understand what needs to be done to ensure satisfactory performance for your feeder. Okay, next slide. The next step in the distribution planning process is risk analysis, as you see from the graphic. This activity identifies the feeders and the substation transformers that are at risk of being overloaded on the system intact conditions or N-1 conditions, or during a contingency, system intact N-0 conditions, or during a contingency N-1 conditions. The total number of risks generally exceeds what can be mitigated with available funds. So that means some kind of budget constraint planning process needs to be applied. And the planner must strike a balance between a number of factors that could be in tension. The risk must be mitigated. At the same time, you have to plan for new customers who are coming online. You have to address aging, and you also need to prepare for the future and evolve the system to meet new types of non-traditional loads. So on the next slide, I show you an example from a system study that was done in 2016. The study was done for a focused study area that included several feeders from a substation. The left chart shows the circuits that are at risk of being overloaded during N-0 or system intact conditions in 2016. The right chart shows the circuits that are at risk of overloading under normal conditions 20 years later in 2036, based on the load forecast. So based on the forecast that we saw before, projecting the load into the future, 20 years, we see that there is a lot more red on the right chart, which means in total there are 4 additional circuits that are at risk of severe overloading in 20 years if the load continues to grow in correlation with the forecast. And so this exposes now the triggers for doing something to mitigate those risks. The next chart shows the risk on the N-1 conditions, which are the conditions. Sorry, next chart, Kerry. Right, so on the next chart, the N-1 risk is the risk of overloading after a feeder has failed. And as we discussed before, when a feeder has failed, you would transfer customers from the failed feeder to adjacent feeders. Well, when you do that, now you begin to expose weaknesses in the system. And this shows that based on the load forecast from 2016 to 2036, there will be several more circuits. In fact, 2 additional circuits would be in red, as the bottom chart shows. And you see there's a lot more red spread around the system. So this is a very eye-opening chart and shows the risk that must be mitigated. How many time?
Lavelle, you have about 15 minutes left, so I think you should push on.
Okay, so let's keep going. And so mitigation plans now would be developed to meet those risks. And those plans would be looking at the N-0 and the N-1 thresholds. On the next slide, Carrie shows, I'm on slide 20 now. That's right. It shows that there's a process for doing this, and the process includes straightforward and localized solutions, and anything that requires a more extensive measure would lead to a planning study to develop the solutions. Next slide. So the planning study evaluates alternatives and potential solutions. And the potential solutions could be reinforcing the existing feeders, that means upgrading the conductors, adding or extending new circuits, expanding the substation, more expensive options certainly, adding a new transformer to the substation, or evaluating alternative sources to bring into the system, such as building a whole new transformer. So the measures could go from the very basic and less expensive to more expensive solutions if the basic ones do not meet, they don't mitigate the risk. DER has not historically been considered a viable alternative by this utility, but due to the reduction in costs and other regulatory mandates, it's now becoming a solution that may have a future. And I'll talk about that in a little bit. The next step is the budget creation that is being shown here. Several factors are used to prioritize the solutions, the reliability, the safety, environmental and legal aspects, which tend to be more highly rated than the other two. Anything environmental or legal tends to take precedence. And then the financial efficacy of the solutions. Oh, is there a question?
No, so, just a second, sorry.
Okay, I think at this point there's a poll question if you want to put it up. I know we don't have a lot of time.
Yeah, it's after, you said after slide 26, so we can move.
All right. And so the next step is a project initiation. After the solutions are developed and they are ranked and prioritized by the constrained budget, then the projects are initiated by the distribution planning department. And then finally, on the next slide, they go to design and construction. Much of the distribution planning that I've talked about, I'm now on slide 25, Carrie. I'm kind of skipping ahead. Much of the distribution planning process I've talked about requires tools and applications. And if you notice on each of those slides, and maybe you didn't notice because we went through those a little bit quickly, but on each of those slides, I identify the tools that are used by the planners. The planning engineers rely on these tools, which could be in-house tools or commercial tools, to perform the annual forecasting and the system assessment. But Xcel has seen that there is a need for advanced planning capability, specifically to facilitate integration of DER, analysis for non-wise alternatives, scenario analysis, more granular forecasting. And as part of the AGIS initiative, they have embarked on developing an advanced planning capability and included that in the 5-year investment plan. Next slide. Next slide basically shows the evolution of tools. It summarizes the evolution from the traditional tools to the advanced planning tools that will replace the distribution asset analysis system, which is used for forecasting. This tool will also add advanced DER planning functionality, as I mentioned, and Debbie Lou will discuss these in the next presentation. But these include scenario planning, locational net benefits analysis, and so forth. And this is the trajectory that Xcel is on. Okay, great. So next slide. For the next couple of slides, I'll talk about non-wise alternatives. I'll maybe take 5 minutes to go through this. And I will give a few examples of how Xcel Energy plans to incorporate non-wise alternatives into its planning portfolio. But before that, there's a poll. The distribution planning process typically includes which of the following activities: mitigating risk of overloads, planning for new customers, addressing asset aging, preparing for the future, or all of the above. Take a few minutes to record your responses. Excellent. I have been completely clear. 100% have got it. Thank you. So yes, all of those are important, and of course there are trade-offs between them, but they're all targets for the distribution planning activity. Okay, so non-wise alternatives. Next slide. Non-wise alternatives, NWA, are emerging as another viable alternative for resolving risk issues on the distribution system, particularly as the DER costs decrease. And the graphic that's inserted here shows the drop in the cost of battery storage over time. One thing that must be considered is the difference between traditional build-out solutions and non-traditional solutions, such as DER. And this is where the rubber meets the road. How will the utility basically resolve the characteristics of non-wise alternatives based on technology, location, time of day, and apply these in the traditional solutions? So niche applications are seen as suitable for NWA. They're quickly becoming cost competitive. The next slide, I will quickly just show you Xcel's opinion. Bottom line is they see capacity projects as the preferred application for non-wise alternatives. That is, projects that would reduce overloads on the system. For example, on the next slide, it shows you on the N-0 conditions, a feeder is overloaded at about 0.71 megawatts overloaded for a little bit over an hour, so is 1 megawatt hour of energy at risk. Assuming a battery costs $400,000 per megawatt hour, this means that a DER costing $400,000 can be applied to mitigate that risk. This is cost competitive with a typical mitigation project, such as upgrading the feeder or extending the feeder and transferring load to another feeder. And so non-wise alternative is seen as maybe an appropriate or a cost-effective alternative for this type of project. The next one shows another example, but now with an N-1 on N-1 conditions. In this case, the feeder is overloaded 4 megawatts because load is being transferred to it. It's overloaded for about 6 hours, so about 24 megawatt hours of energy. This would need a much bigger battery, of course, and if you're talking about battery, and we're using the same $400,000 a megawatt hour price, we see that the cost is about $9.6 million, which is orders of magnitude higher than a typical mitigation project, such as upgrading the feeder or extending or transferring load to an additional feeder. And so the bottom line is there is a place for non-wise alternatives, but when it gets to a lot of energy, then you have to weigh this against the effectiveness of other solutions. Next slide, sorry. And so this shows the screening process. Basically, they're looking at capacity project types, and they're looking at particularly N-0 risk mitigation and some N-1. Time frame is the 2022 to 2024 time frame. So up to this point, we've been talking primarily about risk of equipment overloads. I just want to give you a quick flavor of some other very important distribution planning imperatives around asset health and reliability management. Standards are important. Here are some common standards that are used. They're important for what is acceptable, what is customary, what is permissible in planning and designing the system. I don't want to talk about standards because it could be very exhaustive. Next slide shows asset health is concerned with monitoring and addressing the state of the distribution system. This is critical to providing reliability for overhead and underground systems. The two inserted charts are examples of how tracking assets, even tracking the age of assets, can help you improve reliability. In the top chart, the age of poles is correlated with the failure rate of the poles. So the older the pole, the more likely it is to fail. And simply by tracking the age of the assets, you can identify where reliability issues are. The bottom chart shows that the age of cables and how often you replace the cables impacts reliability. And so this shows the number of cable replacements over years, and it shows that the SAIFI, I think in this case it's the SAIFI, is falling. The annual failures is reducing as the number of cable replacements is increasing, which again shows you the bottom line that asset replacement and keeping asset health is essential for reliability. Next slide. Xcel, as many typical utilities do, have many asset health programs. They're listed here. The capital budget for Xcel is over $80 million a year for asset health, and O&M $1.5 million per year. And so this translates into a pretty big number when you look at the 5-year investment plan. The details are shown in the extra slides, but I just wanted to give you an idea of how important this is to the utility based on its budget allocation. The next slide shows, actually you can skip to slide 2038. Xcel's reliability is in the second quartile of the IEEE reliability benchmarking survey. So they typically exceed their quality of service targets. In the chart, you see the blue line is the Minnesota quality of service target for the utility, and the red line is the reliability in 2018. So they're doing really well. Next one, it shows for SAIFI. And Xcel is doing this because they have a strong reliability management program that identifies the poorest performing feeders each year and does analysis to rectify those, identifies protective devices that operate often, and also identifies customers that experience multiple interruptions and perform studies to find mitigation solutions for those customers. And those solutions are ranked against the overload solutions in the budget. So this is how reliability and capacity overload projects tend to fight for some of the same money. So finally, Carrie, let's jump to slide. Yeah, so this one just shows a chart that how the reliability projects are ranked together on the same sheet, and then investment decisions are made to identify which one gives the greatest benefit for the lowest cost. The next slide. Finally, I want to discuss briefly grid modernization initiatives. These are leveraged for advanced distribution planning. I have often said, and I'm going to repeat it, that good distribution planning starts with muddy boots, fundamental, foundational, traditional programs, such as we have been discussing for the last couple of minutes. Only after this can grid modernization technology be applied and be effective for improving the customer experience. That being said, modernizing the grid to make it smarter and more resilient through the use of cutting-edge technologies, equipment, controls that communicate and work together is essential for delivering electricity more reliably and efficiently. This is from the DOE, and it's still true today. Some of the utility-facing technologies that we're seeing are listed here. ADMS is one of the ones that are seen as being core and foundational to the utility achieving the grid modernization objectives. On the next slide, we show that the DMS, or the ADMS, which stands for Advanced Distribution Management System, is core technology that integrates many operational components from other technologies such as OMS, Outage Management System, GIS, Geographical Information System, SCADA, which is the communication system, and DERMS, which is Distributed Energy Resource Management System. The ADMS enables these advanced applications such as FLISR, fault location, isolation, service restoration, which you have discussed previously, and vulnerable optimization to actually occur. It allows a centralized decision making, and it facilitates the development and integration of customized applications on the utility system. So it is a foundational technology for grid modernization, to say the least. The next slide. So Xcel's grid modernization goals are encapsulated in the Advanced Grid Intelligence and Security Initiative, so-called AGIS, which aims to transform the customer experience, to improve core capabilities, and importantly, to integrate grid non-wise alternatives, DER, and advanced forecasting initiatives. The next slide shows the 15-year Advanced Grid Initiatives Roadmap, so-called AGIS. And the thing to note about this, I think Paul DiMartini may have showed this yesterday. The first 5 years of this includes the IDP, the so-called Integrated Distribution Plan. And you can see that the advanced planning tool is part of that. And then the things that are in blue, which tend to be the more potential future initiatives, will be incorporated over the next 10 to 15 years, which are more of the grid modernization technologies. So the long-term focus is on continuing to provide reliable, safe service and advancing the grid at the speed of value, which is a very nice term, by incorporating grid modernization initiatives. Next slide, Carrie, which I think is the last slide, or second to last slide. Grid modernization provides a roadmap for building on the traditional distribution planning and incorporating advanced planning features to address DER and other non-traditional solutions. So this is what this chart is showing. We're basically traversing from the traditional, moving up to using grid modernization to advance distribution planning, which Debbie Lou will talk about in a few minutes. On my final slide, the key takeaways, there's about $2.7 billion with a B, in capital and O&M spending projected over the next 5 to 6 years. 1/4 of this is on grid modernization, or AGIS, and the details of this are in the extra slides which you have. The investments in the physical grid infrastructure, the poles, the wires, the transformers, the relays, etc., provide the necessary foundation for upgrading the grid capabilities. And without this foundation, reliable service would not be provided. The grid modernization goals are built on top of this, and they cannot fully be met if the new technology is deployed on existing or aging infrastructure. So first things first, and then we do the next thing. They must incorporate and coordinate advanced capabilities with the physical grid infrastructure And this will allow advanced communications and intelligent applications to manage the grid as fully integrated bidirectional system. So that's my last slide. I won't go through the extra slides, of course. I can take any questions that you have now.
Thanks, Lavelle. We are just going to let you do the last poll that you have here. The question reads, which of the following is not, that's it, that's the question. Yep. Which of the following is not a utility-facing grid modernization technology? ADMS, electric vehicles, SCADA, OMS, or FLISR? We'll give you a moment to answer that. We did have one question come in, but it seems like you answered it towards the end of your presentation. So I think that we are a little bit over. We'll let this poll close, and then Lavelle, if you just had any final last words, and then I'll introduce Lisa, who's going to introduce Debbie.
Yeah. So the last word basically is so this is a really good setup for Debbie's presentation, where she's going to go deep into the advanced distribution planning initiatives, which again are enabled by having these foundational aspects. And the poll, as the answer is shown, that EV. So the actual answer is electric vehicles is not a grid-facing technology. All the others are. Electric vehicles is more of a customer side, customer-facing technology. So thank you very much. And if you have any other questions that you want to send by email, certainly open to them. My email is here. My contact number is there. Thank you, and have a very pleasant rest of your day.